This video is designed to help you understand how to apply the multiplication principle when repeats are allowed and repeats are not allowed. Let's take a basic case. If you have the digits 1, 2, and 3 and you're going to make a three-digit number, how many different numbers could you make? So the multiplication principle basically says if you can tell how many ways that you can fill the number 1 slot, or the leftmost slot in the digit, how many ways you can fill the second slot or the middle slot in the three-digit number, and how many ways you can fill the third slot in the three-digit number. If you multiply each of those together, you will get the answer of how many different numbers, or let's say combinations, you could make for a 3 different combination lock. So we've said that we can use the digits 1, 2, or 3 in any of the spots. So that means we have 3 choices, or 3 ways we can choose the first digit, or the leftmost digit. We have 3 ways we can choose the second or middle digit, and we have 3 ways we can choose the third digit. This corresponds to having a decision tree, or a tree that tells you what's going on, that says here's the first digit, and you could put 1, 2, 2, or 3 in the first digit. Off of each of those digits you can put 1, 2, or 3. Off of each of the middle digits you can put 1, 2, or 3, and off of each of the last digits you can put 1, 2, or 3. And off of each of those you could put 3 different digits. And this, of course, this pattern repeats along the way. What that means is every path through this tree is a different 3-digit number that you've produced. And of course this tree is uniform, and it's easy to count the number of paths through this tree by simply saying, well, there's 3 choices on the first level, and off of each of those there's 3 choices on the next level, and off of each of those there's 3 choices on the next level. So that means there's 3 times 3, which is 9 paths through the first 2 levels, and then off each of those is 3 more. So that is, of course, a total of 27 choices for this path, for 27 paths through here, which means there's 27 different numbers you could produce. Now, this is what is known as with repeats, or with repeats allowed. And of course what that means is, if you look at the tree, you could have the 3-digit number 111. You could also, that would be corresponding to going down this path right here. So you would go to here, you would choose this one, and then you would choose this one, and that would be the digit 111. You could also have the digit 122, which would mean that you'd be actually coming down through the second path here. If we remind ourselves that these are these paths. So that would be going 1, 2, 2. That's a repeat of 2, and it is a distinct 3-digit number from choosing 2, 2, and then the first one off of that for 1. So order matters, of course. Otherwise it's a different 3-digit number. 1, 2, 2 is a different number than 2, 2, 1. So this would be the idea of allowing repeats. Now, if you were to not allow repeats, your tree is going to look a little bit different. In your first number, your leftmost digit, you have 3 choices. But then in your secondmost digit, since you've used up a choice in your first digit, you would only have 2 choices. And finally, when you get to the third digit, you really don't have a choice. You've used up 2 digits already, So you simply have the third digit. So you have one choice. What that means is you would only have 6 paths through this. What does this tree look like? This tree looks like choose 1, 2, or 3 for the first path. Choose 1, 2, or 3 here. Choose 1 or 3 here. Choose 1 or 2 here. And then off of each of these, there's only one remaining digit that you can use. So if you've chosen 1 for the leftmost, 2 for the middle, 3 must be the last digit. If you chose 1 and 3, then 2 must be the last digit, and so on. Okay? So clearly that limits your choices with this no repeats. So this is without repeats. I'll abbreviate it as W/out, without repeats. And this has a specific name to it, which we'll describe in the next section, in the next slide. But you'll notice that it counts down as you're going. So it says you have 3 choices, then 2 choices, then 1 choice. Each time you've made a choice, you have 1 fewer choices each time. So what this allows you to do is notate this as 3 factorial, because 3 factorial means 3 times 2 times 1. That's a useful shorthand for writing that you're counting down. So this is actually called a permutation. And what that means is counting 3 things taken 3 at a time. In other words, you're using all 3 of them to make your combination lock or make your number. So there's 6 different numbers you can make with the 3 digits if repeats are not allowed, and there's 27 if repeats are allowed. Let's take a look on the next slide at some variations on this. So here's a classic combination lock question. How many possible combinations are there in a lock that has 4 digits, each of which can be 0 through 9? So it's a 4-digit number. The first or leftmost digit we'll call number 1, number 2, number 3, and number 4. Of course, order matters. It's a different digit if it's 1, 2, 3, 4 than if it's 4, 3, 1, 2 or something like that. So we can label them as distinct places to make some choices. In the first case, if we can have 0 through 9, that's 10 choices. What that means is we have 10 choices for the first number, for the first digit. If the second digit is allowed to be a repeat, then we have 10 choices. Once again, we have 10 choices, and for the last digit, we have 10 choices. What this means is we have 10 to the 4th, or 10,000 different combination locks, different combinations that we could get with this lock with 4 digits if repeats are allowed. So we'll call that part A, and we'll say for part B, what if repeats are not allowed? So this is going to give you a different total, and we'll take a look at this, and this is going to be exactly the same setup in that we have a first digit, a second digit, a third digit, and a fourth digit. But now, once we've chosen that first digit, as on the previous slide, we have 1 fewer choices, which means we have 9 choices for the second digit, 8 choices for the third digit, and 7 choices for the last digit. Now, of course, we haven't used up all the digits in this case because there's 10 choices for each one, and it's only a 4-digit combination lock. So what that means is we have digits left over that we haven't chosen, and this can be accounted for using the factorial notation by saying, oh, this is essentially 10 factorial, but we're cutting off the tail of the 6 digits, the 6 times 5 times 4 times 3 times 2 times 1 after it. So this is the notation. This is known as the permutation of 10 things taken 4 at a time. It's typically written this way or this way, 10 permutation of 10 things taken 4 at a time. And of course, then the formula is going to be that it is 10 factorial over 10 minus 4 factorial, since we're not cutting off the first 4 digits, we're only cutting off the remaining digits. How many are remaining? 10 minus 4. So if we look at the general notation here, this is normally called PNR, or the permutation of n things taken r at a time, and that is n factorial over n minus r factorial. And you'll notice how that fits our pattern above. So let's take a look at one more slide and look at another example of how this can be applied and see if we can write the combination. And of course you can multiply this out. You can simply take this set of numbers, 10 times 9 times 8 times 7, and multiply it out. You don't have to use the fancy formula. But you can also represent it and simply say, oh, this is obviously the permutation of 10 things, choosing 4 of them to be in slots, in 4 spots, where order matters. So let's take a look at another example on the next slide. So here's a question. How many different photos can be taken of 4 students from a 10-student class if they are lined up in 4 chairs in a row? So what we're saying is there are 4 chairs, so we'll call it the leftmost chair or the number 1 chair, the number 2 chair, the number 3 chair, and the number 4 chair. And we're looking at this and we have to decide, are repeats allowed or not? So if there are 10 students in this class and we're going to choose 4 of them to be in this photo sitting in these 4 chairs in a row, how many different photos can there be? Of course, we're ignoring making funny faces or, sitting differently or crossing your legs or whatever. All we're concerned about it, we're calling it a different photo if there's either different people in the photo or they're sitting in a different order. So order matters. So we're going to say order matters in this one. So order matters. But what we have to decide is, are there any repeats allowed? And of course there aren't, because you couldn't have the same student sitting in 4 different chairs or 2 different chairs. Once you've chosen the student to sit in a chair, there are only 9 other students that you can have. So this is like our previous example of the combination lock where repeats were not allowed. So this is no repeats, and that's something that you have to decide from the context of the problem. And it makes sense that in this case, unless you Photoshop somebody in, you're really choosing 4 different students, and so there won't be any repeats. And what that means then is we have our classic 10 choices for the first chair, 9 choices for the second, 8 choices for the third, and 7 choices for the 4th chair. And of course then what this is the permutation of 10 students chosen to be in a photo with 4 at a time. So it's 10 permutation of 10 students 4 at a time, which is going to be 10 factorial over 10 minus 4 factorial, 10 minus 4, and that's factorial, so of course it's 10 factorial over 6 factorial, which is basically simply saying, and let's write this out. So 10 factorial over 6 factorial is actually 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 6 times 5 times 4 times 3 times 2 times 1. What that allows us to do is simply cancel these guys, and of course we get our original numbers of 10 times 9 times 8 times 7, whatever that multiplies out to be. So I hope this has helped to decide to understand the situation of what a permutation is. It's where order matters and there are no repeats, and order matters. Okay, and that's called a permutation. And it has this formal way of counting it, which is useful. You can find this on your scientific calculator once you've figured out how to input the proper numbers in the proper order. But you can always just simply count this as 10 times 9 times 8 times 7. I hope this has helped.